There is a number that astronomers use to agree on. Not exactly, not to the decimal, but close enough that it appeared in textbooks, in documentaries, in the opening lines of lectures given to first-year physics students in universities on every continent. The number was 13.8 billion. 13.8 billion years, the age of the observable universe, the time elapsed since the moment of the Big Bang, the total duration of everything that has ever existed. It was the kind of number that felt settled, foundational, the sort of fact you learn once and carry with you forever, the way you carry the speed of light or the number of planets or the distance from the Earth to the Sun. And then the James Webb Space Telescope turned on. What happened next did not make the front pages of most newspapers. It did not interrupt television broadcasts or trend on social media for more than a day or two. The finding emerged, as most scientific revisions do, slowly, in preprint papers, in press releases from observatories, in careful language from astronomers who were themselves not entirely sure what they were looking at. But over the course of several months, as more data came in, as more teams ran the numbers independently and arrived at the same conclusions, the picture began to sharpen into something that could no longer be explained away or set aside as an outlier. The universe, it turned out, had been doing things earlier than we thought. Galaxies had been forming faster, growing larger, burning brighter, and dying sooner than our best models had ever predicted. Stars had been igniting in the deep past at a pace that our understanding of physics could not fully account for. And because the universe had been doing all of this more quickly, the downstream consequences, the timeline of what comes next, the schedule on which certain inevitable events will unfold, had to be recalculated. Not dramatically, not overnight, not with the kind of sudden finality that makes for a clean headline. But the revision was real, and it was significant, and when you sit with it long enough, when you follow its implications outward into the future, and ask what it means for the life expectancy of stars and planets and galaxies, and ultimately for any conceivable form of life in this universe, the number you arrive at is stark. 2 billion years. That is how much shorter our timeline may be. Not the timeline of human civilization. That story operates on scales of thousands of years at most, and cosmic events will not touch it within any time frame a human mind can meaningfully inhabit. But the timeline of the universe as a habitable place, the window during which stars can burn and planets can orbit them, and the conditions necessary for biology, can theoretically exist somewhere. That window appears to be narrower than we believed, by roughly 2 billion years. To understand why that matters, you have to understand what the James Webb Space Telescope actually is and what it was built to do, and why the things it found in its first years of operation were so unexpected. Not unexpected in the way that surprises a child, not the gasp of seeing something impossible, but unexpected in the way that forces a physicist to sit down and ask whether the equations they have built their career on are missing something important. The telescope launched on Christmas Day of 2021. It had been in development for decades, delayed repeatedly, over budget significantly, the subject of political fights and bureaucratic near cancellations that made it one of the most controversial scientific projects in NASA's history. When it finally reached its destination, a gravitationally stable point in space roughly 1 million miles from Earth, called the second Lagrange point, and when its enormous gold-coated mirror segments unfolded and locked into alignment, and when its instruments cooled to the operating temperatures just a few degrees above absolute zero that they required to function, the scientific community held its breath. The first images came back in July of 2022. They were extraordinary even by the standards of people who look at images of space for a living. The colours were partly artificial, translated from infrared wavelengths that human eyes cannot detect into the visible spectrum, so that we could see what the telescope was seeing. But the structures were real, the galaxies were real, the distances were real, and some of what was visible in those earliest images was already hinting at something that would take months to fully articulate. There were galaxies in those images that should not have been there, not in the sense that they violated any physical law, but in the sense that our models, the carefully constructed, extensively tested, peer-reviewed models of how the universe forms structure over time, did not predict that galaxies of that size and brightness should exist that far back in time. The James Webb Space Telescope was designed to see further into the past than any instrument before it, because when you look at distant objects in space, you are looking backward in time. The light from a galaxy 10 billion light-years away has been travelling for 10 billion years to reach us, which means we see it as it was 10 billion years ago, not as it is now. Webb could see further than Hubble. It could detect fainter signals, resolve finer structures, peer into earlier epochs of cosmic history. And what it found in those earliest epochs did not match the predictions. The galaxies were too massive, too bright, too well-formed. They looked like galaxies that belonged in a universe that had been running for much longer than the universe had been running at the point in time when we were observing them. It was as though you opened a photo album from someone's first birthday party and found pictures of a fully grown adult. Astronomers call these objects massive early galaxies, and they became one of the dominant topics of conversation in astrophysics through 2022 and 2023. Dozens of papers were published. The findings were scrutinized, contested, replicated, and refined. Some turned out to be artifacts, objects that looked further away than they were, or galaxies whose brightness had been overestimated, but many held up. The core observation that early star formation happened faster and more efficiently than our models predicted proved to be robust. To grasp what this means, you need to understand how stars form, and why their formation rate in the early universe is so consequential for everything that follows. Stars are not static objects. They are engines, nuclear furnaces that convert hydrogen into helium and release enormous quantities of energy in the process. Every star in the universe is doing this, has been doing this since it ignited, and will continue doing it until its hydrogen runs out. When the hydrogen runs out, the star changes. It may expand into a red giant. It may explode as a supernova. It may collapse into a neutron star or a white dwarf, or, if it is massive enough, a black hole. These processes take time, different amounts of time depending on the mass of the star, and they follow predictable sequences that astronomers have mapped in extraordinary detail. But stars need raw material to form in the first place. They need clouds of gas, primarily hydrogen, dense enough that gravity can pull them together, compress them, heat them, and eventually ignite nuclear fusion at their cores. In the early universe, the supply of this raw material was abundant. The cosmos was denser then, the gas clouds more numerous, the conditions for star formation more favorable in certain respects. The question our models tried to answer was, how quickly did stars form? At what rate did the universe convert its raw hydrogen into burning stellar engines? And for decades, those models gave us answers that seemed consistent with everything we observed. The James Webb data suggested the models were wrong. Not wrong about the physics, the nuclear reactions, the gravitational dynamics, the spectral signatures. Those held up. What seemed wrong was the timing. Stars in the early universe formed more efficiently than we thought. The rate at which gas converted to stars in those first few 100 million years was higher, and this has consequences that cascade forward through all of cosmic time. Here is why. The universe has a finite supply of hydrogen. It was created in the first few minutes after the Big Bang in a process called Big Bang nucleosynthesis. And while stars produce helium and heavier elements through fusion, and while supernovae scatter those elements into interstellar space where they can be incorporated into new stars and new planets, the total amount of hydrogen available to make new stars is not unlimited. It is a budget. And that budget is being spent. Every star that forms is drawing from that budget. Every stellar nursery that ignites is consuming gas that will not be available for future star formation. The question of when the universe runs out of star-forming material, when the last stellar nurseries go dark and the last stars ignite and begin their long, slow fade toward extinction, is fundamentally a question of how quickly the budget is being spent. If the spending rate in the early universe was higher than we thought, if stars were forming faster in those first billion years than our models predicted, then the budget depletes sooner. The last stars arrive on schedule a little earlier. The universe goes dark a little ahead of plan, 2 billion years earlier, according to some estimates. Now, it is important to be precise here, because the numbers involved are so large that context is everything. The universe is 13.8 billion years old. The last stars, the small, cool, extremely long-lived red dwarf stars that will outlast everything else, are expected to burn for trillions of years into the future. We are talking about a timeline that extends tens of trillions of years beyond the present moment. 2 billion years off the end of a 100 trillion year window is, in one sense, a rounding error. It is roughly 2% of the total stellar lifespan remaining. But that framing misses the point. The point is not the percentage. The point is what those 2 billion years represent. What could happen in them, what kinds of processes they contain, what possibilities they open or foreclose. And the deeper point is what the revision tells us about our models, about what we did not know, and about how many other things we may not yet know. Because the James Webb Space Telescope has only been operational for a few years, it is still collecting data. The early galaxy findings are among its most discussed results, but they are not its only surprises. With each observing cycle, with each new data set released to the global astronomical community, new anomalies surface. New questions that the models did not anticipate, new evidence that the early universe was doing things we did not expect, on timescales we had not accounted for. We are, in a very real sense, in the middle of a revision, not a revolution. The basic framework of cosmology is not being overturned. The Big Bang happened. The universe is approximately 13.8 billion years old. The laws of physics we have established are not breaking down. But within that framework, within those confirmed foundations, something is being adjusted. The schedule is being updated. The timeline is being rewritten. And when you ask what that rewriting means, not just for academic astrophysics, not just for the careers of cosmologists, but for the long arc of everything, for the future of stars and planets and any life that might exist on them anywhere in this enormous and mostly empty universe, the answer requires going back to the beginning. Not the beginning of the telescope, not the beginning of the research program or the funding debates or the engineering challenges, the actual beginning. 13.8 billion years ago, the universe came into existence. The physics of that moment, the precise mechanism, the cause, if there was a cause, the nature of the singularity or the quantum fluctuation or whatever it is that cosmologists have not yet agreed upon, those questions remain open. But what happened in the moments and years and millions of years after that first instant is mapped with extraordinary precision. The universe expanded. It cooled. Protons and neutrons formed in the first seconds. Atomic nuclei formed in the first few minutes. Atoms, mostly hydrogen, some helium, traces of lithium, formed about 380,000 years in, when the universe cooled enough for electrons to settle into stable orbits. After that came the cosmic dark ages. For perhaps 150 to 200 million years, the universe was dark. There were no stars, there were no galaxies, there was only the slow, patient, gravitational gathering of hydrogen gas into the denser regions of space, pulled by the slight variations in density that had been seeded in the first moments after the Big Bang. Everywhere was dark. Everywhere was cold. Everywhere was the same quiet process of matter falling toward itself. And then the first star ignited. We do not know exactly when. We do not know its exact mass or location. We have never directly observed it. It was likely a massive, short-lived star, perhaps hundreds of times the mass of our Sun, burning fast and bright and dying in a supernova within a few million years. But its ignition, and the ignition of the countless stars that followed it in those first hundreds of millions of years, marked the end of the cosmic dark ages and the beginning of the epoch of Ryanization. The James Webb Space Telescope was designed in significant part to see this epoch, to observe the first galaxies forming during and after the cosmic dark ages, to study the first generations of stars, to understand how structure emerged from the uniform darkness of the early universe. And it succeeded. It saw further than any telescope before it. It found galaxies from earlier in cosmic time than we had directly observed, and what it found there changed the schedule. This is where we begin. The universe has a plan. Not in any conscious or intentional sense. The universe does not plan, does not want, does not know. But it has a trajectory, a direction implied by its initial conditions and the laws of physics that govern it. That trajectory has been the subject of human inquiry for thousands of years, and in the last century it has become the subject of precise mathematical modelling, observational testing, and increasingly confident prediction. We thought we knew that plan fairly well. We thought we had the timeline roughly right. The James Webb Space Telescope suggests we were off. By how much and in which direction and what it means for the billions of years still to come. That is the story we are going to tell here, in full, from beginning to end through every phase of what the universe will do and when it will do it, accounting for what we now know and what we have recently been forced to revise. It begins, as all cosmic stories do, with light. The light that Webb detected from those distant, unexpectedly massive galaxies had been travelling for over 13 billion years before it entered the telescope's mirror. It left its source when the universe was less than 1 billion years old. It has been crossing the expanding void of intergalactic space ever since, stretching as it travelled, its wavelengths lengthened by the expansion of the universe itself, shifted from visible light into the infrared. into the wavelengths that only Webb's instruments were designed to detect. When it arrived, it carried information about the temperature of the gas that emitted it, about the mass of the stars that heated it, about the age of the galaxy it came from, the rate at which that galaxy was forming new stars, the chemical composition of its interstellar medium. Astronomers read light the way a doctor reads a blood test. Every wavelength tells a story. Every spectral line is a signature. And the stories that the light from those early galaxies told were consistent in their implication. These galaxies were doing too much, too soon. The standard model of cosmology, called lambda CDM for cold, dark matter with a cosmological constant, predicts that early galaxies should be relatively small and irregular. The universe in its youth did not yet have the long time scales required for large, well-organized structures to assemble. Mergers between smaller galaxies, the slow accretion of gas, the complex dynamics of dark matter halos, all of these processes take time. The model predicts a universe that starts small and lumpy and gradually organizes itself into the magnificent spirals and ellipticals we see in the nearby universe. What Webb found in some cases were galaxies that appeared to have skipped several steps, galaxies that looked old, chemically enriched, well-structured, massive, in a universe that was not yet old enough for them to have become that way by the processes our model describes. The tension between observation and prediction was not subtle. Astronomers used words like impossible, always in quotation marks, always with the implicit asterisk that nothing is truly impossible if the physics is real and the data is good, but still to describe what they were seeing. One paper, published in early 2023 and quickly circulated widely in the astronomical community, described a population of galaxies so massive and so early that they would, if confirmed, require the universe to have converted its available gas into stars with nearly perfect efficiency in its first few 100 million years. That kind of efficiency had never been observed in the nearby universe. It contradicted our understanding of how star formation works, of how feedback from young stars and supernovae disrupts the gas clouds and throttles the rate of new star formation. Either something was suppressing that feedback in the early universe, allowing star formation to proceed unchecked at rates we have never seen, or our estimates of the masses of these galaxies were wrong. Both possibilities have been explored. Neither has been definitively ruled out. The data continues to be analyzed. But here is what has become clear from the accumulation of Webb's observations over its first years of operation. The early universe was a more vigorous place than we thought. Star formation happened faster. Galaxies assembled more quickly. The first cosmic chapter, the wild, turbulent, intensely creative period of the universe's youth, was shorter and more productive than our models had predicted. And if the first chapter was shorter and more productive, the remaining chapters are altered as a result. Not the chapters we are living through now, not the next million years, or even the next billion. Human civilization and the sun's remaining lifespan and the geological future of the Earth, none of these are affected by what Webb found. The cosmic consequences operate on timescales that dwarf anything biological, but they are real. They are measurable. And they matter in the way that all the true things matter, because understanding what the universe is actually doing, rather than what we thought it was doing, is how we arrive at a more honest picture of where we are and where everything is headed. The timeline has been updated. The revision is roughly 2 billion years off the far end of the stellar era. that long twilight epoch in the far future when the universe will still contain burning stars and the conditions for warmth and energy, and conceivably life will still exist somewhere. 2 billion years that we thought we had, that our models had penciled in, that we had been counting on as part of the universe's remaining budget, may not be there. What that means in practice requires understanding the full timeline of what was supposed to happen. The original plan, the schedule we believed in before the Webb data arrived. Because only against the background of what we thought we knew can you appreciate what has been revised. That story, the old timeline and the new one, the universe we thought we understood and the universe that Webb is slowly forcing us to see more clearly, is what the next several hours are going to lay out phase by phase, from now until the last light in the cosmos finally fades. We start in the present, in the middle of what astronomers call the stelliferous era, the age of stars, and we trace the timeline forward through its phases, noting at each stage what the original model predicted and where the new observations suggest the schedule needs updating. Then we go back and ask the harder question. If Webb has already forced us to revise the timeline by 2 billion years based on a few years of data, what else might we be missing? What other assumptions are baked into the long-range projections that we have not yet had the tools to test? And what does it mean for all the timelines we have built, the countdowns to stellar death, to the freeze-out of planetary systems, to the heat death of the universe itself, if the foundation those timelines rest on is less certain than we thought? Those are not comfortable questions, but they are the questions that honest cosmology asks, and the James Webb Space Telescope, in its extraordinary gold-mirrored, infrared-seeing way, has made them impossible to ignore. So let's begin with where we are, right now. In the present moment of cosmic time, roughly 13.8 billion years after the beginning, in the middle of the great burning era that has defined the universe for most of its history. Let's stand here and look both ways, back toward the revised origin story that Webb has helped rewrite, and forward toward the revised future that those revisions imply. The clock is running. The budget is being spent, and as of a few years ago, we discovered we may have been reading the meter wrong. To understand what the James Webb revision actually changed, you have to understand what it was revising. You have to hold the original timeline in your mind clearly enough that when the new numbers arrive, you can feel exactly where they land and what they shift. So before we go further into what Webb found and what it means for the future, we need to walk through the timeline that astronomers had constructed before the telescope turned on. The schedule of cosmic events that represented our best understanding of where the universe was going and when. This timeline did not come from a single discovery or a single scientist. It was assembled over decades, built from the contributions of thousands of researchers working across observatories on every continent and in space, using instruments ranging from simple optical telescopes to gamma-ray detectors to gravitational wave observatories. It was tested, refined, argued over, and gradually converged upon. It is, by any honest measure, one of the greatest intellectual achievements in the history of our species, a map of time stretching from the present moment to the incomprehensible depths of the far future, constructed from mathematics and observation and patient inference. It begins where we are now. Right now, 13.8 billion years after the Big Bang, the universe is in what cosmologists call the stelliferous era. The word comes from the Latin for star-bearing, and it is an accurate description. This is the age of stars. The epoch in which the universe is populated by burning nuclear furnaces, billions of them in each of hundreds of billions of galaxies, converting hydrogen into helium and light and heat at a rate that fills the cosmos with energy. The stelliferous era began with the first stars, roughly 200 million years after the Big Bang, and it will last, according to the pre-Webb models, for approximately 100 trillion years into the future. 100 trillion years. The number is so large it resists intuition. Our universe is currently 13.8 billion years old. 100 trillion is roughly 7,000 times that. If the current age of the universe were a single day, the stelliferous era as a whole would last about 19 years. We are in the early morning of the second day. The era has barely started. During this era, stars form, burn, and die in a continuous cycle. The details of that cycle depend heavily on the mass of the star in question, and this is where the story becomes interesting, because not all stars are created equal and not all stars will outlast the era in which we currently live. The most massive stars, the giants, the supergiants, the blazing blue-white monsters that outshine our sun by factors of 1,000,000 or more, live fast and die young. A star 10 times the mass of our Sun will burn through its hydrogen supply in perhaps 20 million years. A star 50 times the mass of our Sun may last only a few million years. These stars are spectacular while they exist, their deaths even more spectacular. Supernovae that briefly outshine entire galaxies, releasing more energy in a few seconds than our Sun will emit across its entire lifetime. But they are transient. They flare and they die, and what they leave behind is either a neutron star or a black hole, and neither of those objects produces the steady warmth that biology requires. Medium-mass stars like our Sun live much longer. The Sun has been burning for approximately 4.6 billion years and has roughly 5 billion years remaining before it exhausts its hydrogen supply. At that point, it will expand into a red giant, cool, shed its outer layers into space as a planetary nebula, and leave behind a white dwarf, a dense, Earth-sized remnant that will slowly cool over billions of years until it fades to darkness. The Sun's total lifespan is approximately 10 billion years, which seems generous until you place it against the full duration of the stelliferous era and realize it represents only 1/10,000th of the age of stars. And then there are the red dwarfs. Red dwarfs are the most common type of star in the universe. They are small, ranging from about 8% to about 50% of the Sun's mass, and they are cool, burning at temperatures that give them their reddish hue and make them invisible to the naked eye from Earth, despite being the most numerous stars in the galaxy. They burn their hydrogen slowly, miserly, at a fraction of the rate of larger stars, and as a consequence, they live for an extraordinary length of time. The least massive red dwarf stars, the ones hovering just above the threshold at which nuclear fusion can be sustained, will burn for approximately 10 trillion years. Some estimates push it higher, 13 trillion, even longer. These are the last stars, when all the sun-like stars have died, when all the giants have exploded and faded, the red dwarfs will still be burning. Dim, cool, unhurried, but burning, providing warmth, maintaining the conditions that, in principle, allow planets to remain geologically and thermally active and to harbour whatever chemistry life requires. This was the backbone of the original timeline. The last stars, the red dwarfs, were the final chapter of the stelliferous era. and they were expected to last until roughly 10 to 100 trillion years from now, depending on mass. After them, nothing new would ignite. The universe's supply of star-forming gas would be exhausted, either consumed by existing stars or too diffuse to gather into the density needed for fusion to begin. The lights would go out one by one over those long trillions of years, until the last red dwarf flickered and died, and the universe entered the next phase, the degenerate era, the age of white dwarfs and neutron stars and cold, dead stellar remnants slowly radiating away the last of their heat into the void. That was the timeline. That was what we thought we were working with. Now, here is where the James Webb revision enters. The stelliferous era does not run on a fixed clock. It runs on a budget, specifically the budget of hydrogen and helium available in the universe for conversion into stars. That budget is not replenished. There is no mechanism by which the universe produces new hydrogen in significant quantities after the Big Bang. What exists is what exists, and it is being consumed on a schedule that depends on the rate of star formation throughout cosmic history. If you spend your budget faster at the beginning, you have less left for the end. This is the core of what the Webb data implies. If star formation in the early universe was more efficient than we modelled, if more of the available gas was converted into stars in those first billion years at rates our pre-Webb models did not predict, then the total inventory of star-forming material available for the far future is somewhat smaller than we calculated. The stars that will form in the distant future, the red dwarfs that will be the last lights in the universe, will form in slightly smaller numbers. Their era will end slightly earlier. The stelliferous era closes a bit ahead of schedule. How much ahead? This is where the estimates cluster around that 2 billion year figure. It is not a precise number. Cosmology does not yet operate at that level of precision for timescales this vast. It is an estimate, an order of magnitude correction derived from the Webb observations and from the updated models of early star formation efficiency that those observations have forced upon us. But the direction of the revision is consistent and robust. The universe is ahead of schedule, and ahead of schedule means finishing sooner. To appreciate why this matters, why 2 billion years off the end of a 100 trillion year era is worth taking seriously, you have to think about what those years represent in terms of possibility. We do not know whether life exists anywhere in the universe beyond Earth. We know that the conditions for life, liquid water, chemical complexity, sources of energy, are not unique to Earth. We know that the universe contains billions of rocky planets orbiting within the habitable zones of their host stars. We know that red dwarf stars, despite their dimness and their tendency toward energetic flares in youth, are the most plentiful stars in the universe and that they host planets in significant numbers. We know that if life is possible anywhere, it is possible around red dwarfs, and that those stars will burn long after the sun has died. The question of whether life could persist in the universe through the full duration of the stelliferous era, whether biology could, in principle, spread to red dwarf systems and endure for trillions of years, is one of the most profound questions in all of science. It touches simultaneously on cosmology, astrobiology, the physics of habitability, and the deepest questions about what life is and what it requires. No one knows the answer, but the question is real, and the timeline matters for asking it honestly. If the stelliferous era is 2 billion years shorter than we thought, if the last red dwarfs die 2 billion years sooner, then the window of possible cosmic habitability is 2 billion years narrower. That is not nothing. 2 billion years is longer than the entire history of complex animal life on Earth. It is 400 times the current age of our species. It is a vast stretch of time within which, if life is possible at all in the far future, a great deal of it could have existed. But there is a subtler point, and it cuts deeper. The Webb data does not only tell us that star formation was faster in the early universe, it tells us that our models were wrong. Not catastrophically wrong. The basic framework stands. The physics is not broken, but wrong in a way that had real consequences for our predictions and wrong in a direction that our models did not anticipate. Which raises the question, what else are the models wrong about? Every timeline we have constructed for the future of the universe rests on a set of assumptions. Assumptions about the rate at which gas is consumed. Assumptions about the efficiency of star formation in different environments. Assumptions about how dark matter halos evolve, how feedback from black holes affects galactic gas reservoirs, how the slow cooling of the intergalactic medium over cosmic time alters the conditions for star formation in the future. These assumptions were tested against observations of the nearby and intermediate distance universe where our data was good. They were extrapolated backward in time to the early universe where our data was limited by the capabilities of the instruments we had before Webb. Webb improved those instruments dramatically. It pushed back the frontier of observation by hundreds of millions of years of cosmic time. And in the newly revealed territory it exposed, the models did not perform as expected. The reasonable response to this is not panic. Science is supposed to work this way. Predictions are made, observations are taken, predictions are revised. The process is functioning correctly. The fact that Webb is generating surprises is not a sign that cosmology is broken. It is a sign that cosmology is alive and progressing. But intellectual honesty requires acknowledging that if the models were wrong about the early universe, they may also be wrong about the future. The same mechanisms, star formation efficiency, gas consumption rates, feedback dynamics that operate in the past will operate in the future. If we were miscalculating them in one direction, we may be miscalculating them in others. This is the deeper implication of the Webb revision, and it runs through everything that follows. Not a single specific 2 billion-year correction, but a general recalibration of our confidence in the long-range predictions. The universe is doing something we did not fully anticipate. The schedule is less certain than we thought. With that in mind, let's return to the timeline, the updated one, now carrying Webb's corrections and the uncertainty they imply, and trace it forward through its phases. We are currently, as established, in the middle of the stelliferous era. The Milky Way galaxy, which contains our solar system, is itself in a relatively active phase of stellar evolution. New stars continue to form in its spiral arms in the dense gas clouds of its star-forming regions. The Sun, our star, is a stable middle-aged G-type main sequence star with roughly 5 billion years of hydrogen-burning life remaining. None of this is immediately altered by the Webb findings. The local present is unaffected. But zoom out. Pull the camera back from our solar system, from our galaxy, to the scale of the observable universe as a whole. And what you see is a cosmos in gradual decline. Star formation rates peaked long ago. The universe forms stars most actively around 2 to 3 billion years after the Big Bang. Cosmologists call this the cosmic noon, the era of maximum stellar activity, when galaxies were most vigorously converting gas to stars, and the night sky, had any observers existed to see it, would have blazed with a density of light unimaginable from our current vantage point. We live roughly 11 billion years after cosmic noon. The rate of star formation in the universe today is approximately 10 times lower than it was at that peak. The universe is winding down its stellar productivity, even now slowly, on timescales too vast to observe within a human lifetime, but measurable across cosmic datasets. This decline will continue. The gas reservoirs that feed star formation are being depleted. The rate at which new stars form will continue to drop, slowly at first, then more steeply, as the available material thins. New stars will still form for a very long time, trillions of years, on the pre-Webb schedule, but the rate will be a shadow of what it once was. The first major milestone in the revised timeline comes not from stellar death, but from galactic collision. In approximately 4.5 billion years, not significantly altered by Webb's findings, because this prediction rests on direct gravitational measurements of the relative velocities of our galaxies, not on star formation models. The Milky Way and the Andromeda Galaxy will collide, or rather, they will merge. The word collision conjures images of impact and destruction, of stars smashing into each other and systems being annihilated, but galaxies are almost entirely empty space. The stars within them are so widely separated that even in the chaotic dance of a galactic merger, the probability of any two individual stars physically colliding is vanishingly small. What happens instead is a gravitational ballet spanning hundreds of millions of years. The two galaxies approach each other. Their outer halos of dark matter interpenetrate first. Tidal forces distort the shapes of both galaxies, pulling streams of stars into long arcs across intergalactic space. The galaxies may pass through each other once, swing apart, then fall back together for a second pass, and a third over the course of perhaps 2 billion years of slow orbital decay, before finally settling into a single merged entity that astronomers have nicknamed Milkomeda. Our solar system will almost certainly survive this merger. The probability of the Sun being ejected from the galaxy or falling into the central black hole is low, though not zero. But our sky will change dramatically over millions of years. The familiar constellations will be distorted as our position in the galaxy shifts, and new shapes will emerge as the two galaxies interweave. For hundreds of millions of years, the night sky of any Earth-like planet in our system, if any observer existed to see it, would be a spectacle of unprecedented richness. Two galactic structures merging, star-forming regions igniting under the gravitational compression of the encounter. The core of Andromeda's supermassive black hole glowing as infalling material heats to incandescence. The merger will trigger new waves of star formation. The gravitational compression of gas clouds in the interacting regions will push some of that gas past the density threshold for stellar ignition, briefly reversing the long-term trend of declining star formation. But this will be a local phenomenon, a temporary pulse, not a cosmic renewal. The gas that forms those new stars will be consumed. The budget will be drawn down further. And after the merger settles, after Milkomeda stabilizes into its new, roughly elliptical shape over the subsequent billions of years, star formation in what was once our galaxy will be even lower than it is today. Around the same time, within a billion years or so of the galactic merger, the Sun will complete its life cycle. In approximately 5 billion years, it will begin to exhaust its core hydrogen supply. It will expand. The outer layers will swell outward, consuming Mercury, then Venus, then possibly Earth, though the precise fate of Earth's surface depends on complex interactions between the expanding solar envelope and our planet's changing orbit that remain a subject of active research. Whether Earth is physically engulfed or merely scorched to sterility, the outcome for any life remaining on its surface is the same. The moderate temperatures, the liquid water, the stable climate that have characterized our planet's habitable phase for billions of years will end. The sun will then shed its outer layers, creating a beautiful but brief planetary nebula, and contract to a white dwarf, a dense, hot, Earth-sized remnant cooling slowly over billions of years. It will radiate for a long time. White dwarfs persist. They cool from white to yellow to orange to red to, eventually, a theoretical black dwarf, a cold, dark, inert ball of crystallized carbon and oxygen drifting silently through space. But they do not sustain the conditions for life. They do not warm planets to livable temperatures on the scales that matter for biology, at least not within any orbits that could maintain the liquid water chemistry we understand life to require. By the time the sun becomes a white dwarf, the universe will be roughly 8 to 10 billion years older than it is today. We will be, at that point, in a cosmos that is perhaps 20 to 23 billion years old. The stelliferous era will still have tens of trillions of years remaining. The red dwarfs will still be burning, faint and steady and patient, in the darkness between the expanding shells of dead and dying galaxies. But even then, the revision implied by the Webb data will be in effect. The gas consumed more rapidly in the early universe will have left a deficit, small in percentage terms, enormous in absolute terms, in the reserves available for late-stage star formation. The red dwarfs that would have formed in those 2 borrowed billion years will not form. Their contribution to the universe's last chapter will be absent. It is tempting, from a human perspective, to ask whether any of this matters. The timescales involved are so vast that they have no practical relevance to any living thing we have ever observed or can meaningfully imagine. The sun will not exhaust its hydrogen for 5 billion years. The last red dwarf will not die for trillions of years. The heat death of the universe is separated from us by an interval of time so long that the current age of the cosmos represents a negligible fraction of it. None of this is coming soon. But there is a version of this question that is worth taking seriously, and it is the version that the James Webb Space Telescope implicitly asked when it returned data that did not match our predictions. The question is not whether any of this matters to us, living in the thin slice of cosmic time we inhabit. The question is whether we understood the universe as well as we thought we did. The answer, clearly, is that we did not. Not entirely, not in the details that matter for long-range prediction. Webb showed us galaxies that were too big, too early. It showed us star formation happening at rates our models did not anticipate. It forced us to revise not just a number, not just the duration of the stelliferous era by 2 billion years, but our confidence in the entire framework of long-range cosmological projection. The timeline is less certain now than it was before the telescope turned on, not more uncertain in a way that invalidates the work. The basic structure holds, the physics is sound, but more uncertain in a way that demands humility. The universe has been running ahead of our predictions, doing things faster than we expected. And in a cosmos that runs on finite reserves of the fuel that makes stars and planets and warmth and any conceivable form of life possible, running ahead of schedule means finishing ahead of schedule. The clock we thought we were reading was running fast. By how much exactly? we are still calculating. The Webb data continues to accumulate. New papers are being published, new observations taken, new models revised. The 2 billion-year estimate is a current best approximation, not a final answer. It may be refined upward, it may be refined downward. The process of revision is ongoing and it may produce further surprises. What is not uncertain, what the data has made clear, is that the early universe was more active, more productive, and more consuming of its own future resources than we believed. The wild, creative youth of the cosmos burned brighter and faster than our models predicted, and the long, slow, twilight future, the age of red dwarfs and cooling white dwarfs and patient, ancient light, will be correspondingly shorter. The question of what happens in that twilight and what the revised timeline says about each of its phases is what the next section of this story will address. We have established where we are and we have established what the revision is. Now, we need to trace it forward, through the death of the sun, through the merger of galaxies, through the slow extinction of the last stars, and ask at each stage what the original model predicted and where the updated schedule now places these events. Because the 2 billion-year correction does not fall in a single place on the timeline. It accumulates, it ripples, it shows up differently in different phases of the future, amplified in some places and subdued in others, by the complex dynamics of how star formation, gas consumption, and stellar lifetimes interact across cosmic time. To see that clearly, we need to go deeper into the future than most people have ever been taken. Not speculatively, not imaginatively, but on the basis of the best physics we have, now updated with the best observations the James Webb Space Telescope has provided. The next phase begins approximately 5 billion years from now with a sound no human ear will ever hear. The last exhale of our star. 5 billion years from now, the sun will begin to die. Not suddenly, not violently, at least not by the standards of stellar death, but in the slow, inevitable way that medium-mass stars conclude their lives, following a sequence so well understood that astronomers can trace it in precise detail from the physics of nuclear reactions and gravitational dynamics alone. We have watched this process in other stars at various stages of completion. We know what the sun will do because we have seen what stars like it have already done. It is not a prediction in the speculative sense. It is a reading of a pattern repeated billions of times across the observable universe. But the sun's death, as significant as it is to everything that depends on it, is not the event that matters most on the revised timeline. It is a prologue, a local event, a personal loss for our solar system, situated within a much larger story about what the universe as a whole is doing in this phase of its existence. To understand why the Webb revision matters at this scale, you have to look not just at the sun, but at the entire population of stars that will still be burning 5 billion years from now, and at what the updated models tell us about how many of them there will be and how much longer they will last. When the sun begins its terminal expansion, the universe will be approximately 18 to 19 billion years old. The Milky Way and Andromeda will have begun their merger, or will be in the middle of it. The rate of star formation across the observable universe will be a small fraction of what it is today. Already low by cosmic noon standards, it will have declined further over those 5 billion years as the available gas in galaxies continues to be consumed or expelled by stellar feedback. New stars will still be forming, but in diminishing numbers. The universe in this era will be noticeably older looking, than it does today, dominated by the light of aging stars, the reddish hues of stars in their later phases, the cooling white light of stellar remnants. The Sun's expansion into a red giant will take place over approximately 1 billion years, beginning roughly 5 billion years from now and completing around 6 billion years from now. During this phase, the Sun's outer envelope will expand to perhaps 100 times its current radius, engulfing the inner planets or coming close enough to them that their surfaces are heated to temperatures far beyond anything that could support any chemistry we would recognize as biological. The habitable zone, the range of orbital distances at which liquid water could exist on a planetary surface, will shift outward. Europa and Ganymede and other icy moons of the outer solar system currently frozen will find themselves suddenly within range of warmth. There is speculation among astrobiologists about whether this brief period, perhaps 100 million years or so, could represent a transient window of habitability for outer solar system bodies. 100 million years is not a long time by the standards of evolutionary biology. Life on Earth required hundreds of millions of years to move from single-celled organisms to complex, multicellular life. Whether 100 million years is enough for any life to emerge in a newly thawed moon is an open question and likely an unanswerable one from our current position in time. But the question itself illustrates something important about how the timeline of stellar death intersects with the question of cosmic habitability. The end of one world is not always the simple extinction of all possibility. Sometimes it is a redistribution, but these are local details. Let's zoom back out to the universe as a whole. The critical event in the middle phase of the stelliferous era is not the death of any individual star. It is the slow but irreversible decline in the universe's capacity to make new ones. This decline is already underway. It has been underway since cosmic noon, roughly 11 billion years ago. The universe has been forming stars at a falling rate ever since that peak, and the trajectory will continue. The reason star formation declines is not complicated in principle, even if the details are subtle. Stars form from cold, dense gas, primarily hydrogen and helium, in molecular clouds. These clouds exist within galaxies fed by the infall of gas from the intergalactic medium. Over time, several processes remove gas from the pool available for star formation. Stars consume it through nuclear fusion. Supernovae and stellar winds inject energy into the surrounding gas, heating it and pushing it outward, making it harder for gravity to compress it back into new stars. Active galactic nuclei, the energetic jets and radiation from supermassive black holes at the centers of galaxies, can heat or even eject gas from galaxies entirely in what astronomers call quenching events. All of these processes reduce the reservoir, and once the reservoir is depleted enough, star formation essentially ceases in a given galaxy, even if traces of gas remain. The galaxy is quenched. Its stellar population ages, its bright young stars die off, and what remains is an aging community of stars slowly working through their lifespans. The Milky Way is not quenched yet. It is still forming stars, though at a declining rate. But many large elliptical galaxies in the nearby universe are effectively quenched already. Their star-forming days are over. They are living off their existing stellar populations, watching their most massive stars die while the less massive ones continue burning, slowly reddening as the blue light of young massive stars fades from their integrated spectra. This is the future of essentially all galaxies, quenching, the cessation of new star birth. the transition from an active, self-renewing stellar community to an aging, declining one. And here is where the Webb revision inserts itself with particular force. The rate at which galaxies quench, the timeline on which star formation ceases in the universe's galactic population, depends directly on how efficiently gas was consumed in the past. A galaxy that converted its gas into stars more efficiently in its early history has less gas remaining for future star formation. It quenches sooner. The lights go out faster. If Webb is correct that early star formation was more efficient across the universe than our models predicted, then the average galaxy, including in principle galaxies like the Milky Way, has been drawing down its reserves faster than we calculated. The budget is tighter. The quenching horizon is closer. This does not mean the Milky Way is about to stop forming stars. We are talking about timescales of billions of years, and the depletion is gradual. But it means that the long tail of star formation we expected, the slow, gentle decline, extending for many trillions of years into the future, may be somewhat steeper, somewhat shorter than we thought. The universe's stellar population will age out faster. The transition from the stelliferous era to the degenerate era will come earlier. Now, let us talk about the red dwarfs, because they are the linchpin of the revised timeline. They are where the 2 billion year correction actually bites. Red dwarf stars, M-type main sequence stars, the smallest and coolest stars capable of sustained hydrogen fusion, are the universe's most abundant and most enduring stellar objects. They constitute roughly 75% of all stars in the Milky Way by number. They are dim enough to be invisible to the naked eye from Earth, despite their ubiquity. Not a single one of the stars visible to the naked eye in the night sky is a red dwarf, but they will be the last stars standing when all the giants and the sun-like stars have burned out and cooled to darkness. The least massive red dwarfs burn so slowly and so efficiently that their calculated lifespans exceed the current age of the universe by factors of hundreds or thousands. A red dwarf with a mass of about 8% of the Sun, close to the minimum required for hydrogen fusion, will burn for approximately 10 trillion years. Some models give longer estimates, approaching 100 trillion years for the most extreme cases. These stars will outlast everything else. They will still be burning when the last sun-like star has become a black dwarf. They will still be burning in a universe so old that the current age of the cosmos is a negligible rounding error in its history. But they will not burn forever. They too will exhaust their hydrogen, and when the last red dwarf finally fades, the stelliferous era ends. Not with a dramatic event, not with an explosion or a collapse or a transformation, but with a quiet dimming. The last star simply ceases to fuse hydrogen. It contracts to a white dwarf, cooling over trillions of years, and the universe enters the degenerate era, the dark age of stellar remnants. The Webb revision affects this end point. If the early universe consumed its hydrogen more rapidly than expected, then less hydrogen was left over for the formation of late-stage red dwarfs. The population of red dwarfs that will form in the distant future from the remaining gas reservoirs of galaxies that have not yet quenched will be somewhat smaller than our models predicted. Fewer red dwarfs means fewer last burning stars. The final phase of the stelliferous era is populated by a slightly thinner community of those ancient, dim, patient lights. And the last one of them dies slightly sooner. By how much? The estimates center on roughly 2 billion years out of a total remaining stelliferous era spanning tens of trillions of years. 2 billion years seems almost negligible. But consider what 2 billion years of red dwarf burning represents. At the luminosities typical of a late-phase red dwarf, dim, yes, but not zero, and steady and reliable, 2 billion years of stellar energy represents an enormous quantity of heat and light. Around any red dwarf, any planet in the right orbital range receives energy continuously for those 2 billion years. Energy drives chemistry. Chemistry, under the right conditions, drives biology. We cannot say whether life would arise around a late-phase red dwarf in the deep future. We do not know whether life is common or rare in the universe, whether it arises quickly wherever conditions permit it, or whether it requires extraordinary coincidences that may have already been used up. We do not know whether the universe has any life in it at all beyond our own world, but the question of how long the conditions for life can theoretically persist is a meaningful one, regardless of whether life is actually there to take advantage of them. And the answer, updated by Webb, is approximately 2 billion years shorter than we thought. While we are in this phase of the story, the deep middle of the stelliferous era, the long decline toward the last stars, there are other events on the original timeline that deserve attention, because the Webb findings interact with them in ways that are subtle, but real. One of the most discussed events in the deep future timeline is the fate of the local group, the collection of galaxies to which the Milky Way and Andromeda belong, along with dozens of smaller satellite galaxies. After the Milky Way and Andromeda merge into Milkomeda over the next several billion years, the larger members of the local group will continue to interact gravitationally. Some of the smaller galaxies will be absorbed into Milkomeda. Others will remain as satellites, orbiting the merged galaxy in increasingly decaying orbits. Over timescales of tens of billions of years, the local group will coalesce. All of its member galaxies will eventually merge into a single large elliptical galaxy, massive, slowly aging, its stellar population maturing toward the end states of stellar evolution. By the time this final merger is complete, star formation in the local group will have essentially ceased. The last molecular clouds will have been disrupted by the merger dynamics, the last gas reserves consumed or expelled. What remains will be a vast, aging collection of stars in their various stages of decline, the most massive long dead, the sun-like stars cooling as white dwarfs, only the red dwarf still burning, faint and ancient and patient. Beyond the local group, the universe's expansion, driven by dark energy, the mysterious component of the cosmos that causes the expansion to accelerate rather than decelerate, will have been isolating us from other galaxy clusters for billions of years. The galaxies that are currently visible to us, the billions of galaxies in the observable universe beyond the local group, will have receded beyond the cosmological horizon. Their light, stretched by the ever-increasing expansion rate, will no longer be able to reach us. The universe will appear to contract to just the local group, and eventually to just Milkomeda, surrounded by an infinite dark void. This is not a new finding, not a Webb revision. It is a consequence of dark energy, which has been understood since the late 1990s. But it matters for the timeline in a specific way. It means that the fate of the universe as experienced from our position in it is entirely determined by what happens within the local group. The trillions of other galaxies, the trillions of other stars, the incomprehensible number of other worlds out there, They will all be permanently beyond our reach and beyond our observation. The universe will be, to any observer in the local group, essentially empty. A dark, cold void with a single large galaxy at its center, aging slowly, its stars dying one by one over trillions of years. That is the picture the original timeline painted. And the Webb revision does not change its shape. It changes its duration. The galaxy is the same. The emptiness is the same. The aging and dying of stars is the same. But the schedule is updated. The last stars die a bit sooner. The transition to the degenerate era arrives a bit earlier. The window during which that final galaxy contains anything burning narrows by 2 billion years. Now, let us talk about what happens when the last red dwarf finally dies. The transition from the stelliferous era to the degenerate era is not a sharp event. It is a gradual fade. The last red dwarfs do not all die at once. They die one by one across billions of years of the far future, each one cooling and contracting to a white dwarf in its own time, according to its own mass and its own rate of hydrogen consumption. The transition is the slow extinguishing of the last fires star by star over a period that itself spans billions of years. But there is a notional endpoint, the death of the very last red dwarf, the final hydrogen-burning star in the universe. Before the Webb revision, that endpoint was placed somewhere in the range of 10 to 100 trillion years from now, depending on the models used and the assumptions about the least massive red dwarfs. After the revision, that endpoint moves earlier, by the 2 billion year correction. Still unimaginably far in the future, but closer than we thought. After it, the degenerate era begins in earnest. The universe is now populated almost entirely by stellar remnants, white dwarfs, neutron stars, black holes, and by any planets or other substellar objects that have survived the deaths of their host stars. White dwarfs cool slowly and persistently. They retain heat for extraordinarily long periods. A newly formed white dwarf is extremely hot, tens of thousands of degrees, but it has no internal energy source, no nuclear reactions sustaining its temperature. It is simply a dense, hot ball of matter, radiating away the energy of its formation and its former stellar life. Over trillions of years, white dwarfs cool. They pass through the temperature ranges at which they could, in principle, warm a closely orbiting planet. There has been research suggesting that white dwarfs in the degenerate era might maintain habitable conditions for planets that migrate to close orbits after their host star's death, conditions that could persist for billions of years as the white dwarf slowly cools through the temperature range conducive to liquid water on a nearby surface. This is speculative and depends on processes that are not fully understood, but the possibility is real enough to have generated peer-reviewed papers and serious scientific discussion. If white dwarfs can support habitable conditions for billions of years in the degenerate era, then the end of the stelliferous era is not necessarily the end of cosmic habitability. The story continues in a darker and colder universe around the cooling remnants of dead stars. And in that story, the Webb revision still matters, because the white dwarfs that form from the last red dwarfs form slightly fewer in number and slightly earlier in time, and the total white dwarf-supported habitability window is correspondingly narrowed. But we are getting ahead of ourselves. We have not yet fully traced the stelliferous era to its close. We have not yet walked through the specific phases of the universe's future between now and the death of the last star. Phase by phase, with the Webb updated schedule attached to each one. That requires going deeper into the numbers, into the specific timescales, the specific events, the specific milestones that the original models identified and that the revised models now place at slightly different positions on the timeline. And it requires engaging honestly with the uncertainty, not hiding the error bars, not pretending the 2 billion-year figure is more precise than it is, but also not dismissing it as insignificant simply because it is small relative to the full duration of the era. Because here is the thing about the timeline that the universe is running on. It is not a schedule that gets revised based on preference or convenience. It does not bend to comfort or to the desire for more time. It runs on physics, on the rates at which nuclear reactions proceed, on the gravitational dynamics of stellar and galactic systems, on the inventory of hydrogen available to fuel the stars. When the observations tell us the inventory is depleted faster than we thought, the timeline moves. It does not ask permission. The James Webb Space Telescope did not find anything malevolent in those distant early galaxies. It did not find a countdown planted by some external force or a warning embedded in the cosmic structure. What it found was simply the truth. The universe, doing what it always does, following its own rules on its own schedule. And the truth, read carefully, told us that the schedule was running ahead of our predictions by 2 billion years at the far end. By an unknown additional margin in other places along the timeline where our models may also be miscalibrated in ways we have not yet detected. The revised future is still vast, still mostly dark and cold and mostly empty, except for the patient burning of red dwarfs and eventually white dwarfs across timescales that reduce the entire history of human civilization to a rounding error in the cosmic ledger. Nothing about the Webb revision makes the universe small. Nothing about it collapses the unimaginable into the merely large. But it makes the universe more honestly understood, and honest understanding is the only kind that serves. In the next phase of this story, we go further, past the death of the last star, into the degenerate era, the long dark age of stellar remnants, where white dwarfs cool and neutron stars spin down and black holes begin their billion-year reign as the dominant objects in a universe that has forgotten what fire felt like. And we ask what the Webb revision means there, in that cold, dark, patient future, and what it means for the final chapters of cosmic time, because the story does not end with the last star. It continues, quietly, slowly, in the dark, and the revised timeline follows it all the way to the end. There is a moment in the far future of the universe that no one will witness. It will not be marked by any observer, recorded by any instrument, or mourned by any mind. It will simply happen, the way all physical events happen, without ceremony or significance beyond the physics itself. A red dwarf star somewhere in the vast and mostly empty darkness of what was once the local group will exhaust the last of its hydrogen fuel. Its core will cool below the threshold of sustained nuclear fusion. The outward pressure of radiation that has held it against gravitational collapse for trillions of years will ease. The star will contract, slowly and quietly, into a white dwarf, a dense, dim, cooling remnant roughly the size of the Earth, carrying within its crystalline interior the memory of all the energy it ever produced. And with that contraction, the stelliferous era will end, not with a bang, not with any sound at all, because sound requires a medium, and the space around that final star will be so thin, so cold, so emptied of gas and dust by the long attrition of cosmic time that no wave could propagate through it. The universe will simply become in that moment a place where nothing is burning anymore, a place where all the fires have gone out. This moment, according to the pre-Webb timeline, was expected somewhere in the range of 10 trillion to 100 trillion years from now. The uncertainty in that range is genuine. It reflects our incomplete knowledge of the mass distribution of red dwarfs, the precise rate at which the least massive ones consume their hydrogen, and the complex feedback processes that govern the formation of new red dwarfs in the far future. The revised timeline incorporating the Webb findings on early star formation efficiency moves that endpoint earlier, not by orders of magnitude, not by trillions of years, by approximately 2 billion years. The last fire goes out 2 billion years sooner than we thought. To a mind accustomed to human timescales, the difference between 10 trillion and 10 trillion minus 2 billion is nearly impossible to feel. Both numbers are incomprehensibly large, but we are not trying to feel the difference the way we feel the difference between a week and a month. We are trying to understand what it means in the physical and potentially biological ledger of the universe. And in those terms, 2 billion years is not a rounding error. It is a chapter, a long, specific, physically eventful chapter of cosmic time. Now, we enter the degenerate era, the era that begins when the last star dies and ends when the last stellar remnant loses its final store of thermal energy, an era that will itself last for timescales that dwarf the stelliferous era by many orders of magnitude. If the stelliferous era is 100 trillion years long, the degenerate era extends for timescales approaching 10 to the 37th power years, a number so large that writing it out requires scientific notation just to avoid absurdity. The stelliferous era, for all its grandeur, will in retrospect be a brief, brilliant, opening chapter in the full history of the universe. But before we go that far, let us look carefully at the transition. At the universe in the period immediately following the death of the last star, in those first few trillion years of the degenerate era, when the white dwarfs left behind by the stellar population are still hot enough to matter. When a star like the Sun dies, it leaves behind a white dwarf. When a red dwarf dies, and here the physics is interesting, it does not immediately leave a white dwarf in the traditional sense. Red dwarfs are fully convective stars, meaning their entire volume of hydrogen is constantly circulated through the core, unlike Sun-like stars which burn hydrogen only in their cores, while the outer layers remain relatively unmixed. This means red dwarfs do not develop the inert helium cores that cause Sun-like stars to expand into red giants. Instead, they burn steadily through essentially all their hydrogen, becoming what astronomers call blue dwarfs as they heat up in their final phases, and then contracting directly to white dwarfs, helium white dwarfs, dense and hot, without passing through a red giant phase. No one has ever observed a red dwarf completing this process, not because it does not happen, but because no red dwarf in the universe has had time to finish yet. The universe is only 13.8 billion years old, and the least massive red dwarfs will burn for trillions of years. Every red dwarf that has ever formed is still burning. The entire population of red dwarf white dwarfs, those final stellar remnants that will populate the degenerate era, does not yet exist. They are future objects, waiting at the ends of a lifetimes longer than the current age of the cosmos. But we can calculate what they will be like, and we can calculate how they will cool, and at what temperatures they will pass through the habitable range for any closely orbiting planet. and how long they will maintain warmth sufficient for liquid water chemistry before cooling below that threshold. A white dwarf begins its post-stellar existence hot, perhaps 20,000 to 80,000 Kelvin depending on its mass and the details of its formation. It has no internal energy source. It is simply a dense ball of carbon and oxygen, or in the case of red dwarf remnants, helium, held up against further gravitational collapse by a quantum mechanical property of electrons called degeneracy pressure. It will cool over time, radiating away its stored thermal energy at a rate that slows as it cools. Hotter white dwarfs radiate more efficiently. Cooler ones radiate more slowly. The process is extremely long. A white dwarf will remain detectable by its thermal radiation for tens of billions of years. It will pass through temperatures warm enough to maintain liquid water on a close orbiting planet for perhaps a few billion years of that cooling curve, depending on the orbital distance and the albedo of the planet in question. Some researchers have proposed that the cooling phase of white dwarfs in the degenerate era could represent a secondary habitable epoch in the universe's history, not as rich or as widespread as the stelliferous era's habitable zones around active stars, but real nonetheless. A slowly cooling white dwarf with a planet in a tight orbit at perhaps 1% of the Earth-Sun distance could maintain surface temperatures in the liquid water range for somewhere between 1 and 8 billion years, depending on the parameters. That is a long time. It is comparable to the duration of Earth's own habitable phase under the Sun. Whether life could arise in such environments, whether the chemistry necessary for biology could function in the gravitational and radiative environment of a close white dwarf orbit, whether tidal locking and X-ray irradiation and other challenges could be overcome, we do not know. But the physical window exists, or rather it existed, in the original timeline. In the revised timeline, white dwarf habitability windows are not directly shortened by the Webb correction. The cooling curves of individual white dwarfs are determined by physics that is not affected by early star formation efficiency, but the number of such white dwarfs is slightly reduced because the slightly smaller population of last-phase red dwarfs produces a slightly smaller population of helium white dwarfs in the early degenerate era. A smaller population of white dwarfs means fewer potentially habitable systems, fewer opportunities. The universe's secondary habitable epoch, already a thin and speculative possibility, is correspondingly thinner. This is the kind of consequence that the Webb revision produces throughout the timeline, not a single dramatic alteration, not the cancellation of any specific event, but a consistent, cumulative narrowing. The universe doing everything it was going to do, but with slightly fewer actors, slightly sooner, slightly less abundantly than the old models predicted. Let us now move deeper into the degenerate era, past the cooling of the white dwarfs, into the truly alien epochs of cosmic time, where the universe barely resembles anything we would recognize. By approximately 10 to the 15th years from now, a quadrillion years, all the white dwarfs will have cooled to temperatures close to the cosmic background radiation. By this point, the cosmic microwave background, the remnant radiation from the Big Bang, will have cooled further due to the continued expansion of the universe, and the universe will be even colder than it is today. The white dwarfs will be cooling toward it. Eventually, theoretically, they become black dwarfs, cold, dark, inert, crystalline objects, but this requires so much time that no black dwarfs exist yet in the current universe, and they will not exist in significant numbers until the universe is many times its current age. The cooling curve is simply too slow. While the white dwarfs are cooling, something else is happening in the degenerate era that will fundamentally transform the structure of the universe: proton decay. If protons decay, and current theoretical physics suggests they should, though experimental detection has not yet confirmed it, placing only lower bounds on the proton lifetime, then all ordinary matter will eventually dissolve. Every atom in every white dwarf, every neutron star, every planet, every rock, every molecule anywhere in the universe will eventually fall apart. The protons within it will decay, releasing energy and ultimately leaving behind only black holes and a thin, diffuse soup of fundamental particles. The theoretical timescale for proton decay, depending on the particle physics model, ranges from around 10 to the 32nd power years to 10 to the 45th power years. These are numbers that no analogy can adequately convey. The entire stelliferous era, 100 trillion years of stellar burning, is less than 0.1% of the shorter proton decay timescale. The universe will have existed for incomprehensibly longer than anything in its current history before the first proton decays become statistically significant, but eventually they do. And once proton decay runs its course, ordinary matter is gone. The universe enters what some cosmologists call the black hole era, a period in which the dominant objects are black holes, the stellar remnants and galactic black holes that have accumulated over cosmic history, and which, unlike ordinary matter, are not subject to proton decay. They persist, they interact, they occasionally merge, and they slowly, very slowly, lose mass through a quantum mechanical process called Hawking radiation. Hawking radiation is one of the most remarkable theoretical predictions in physics. Arising from the intersection of quantum mechanics and general relativity, two theories that do not yet have a fully consistent combined formulation, it predicts that black holes are not perfectly black. They emit a faint thermal radiation caused by quantum fluctuations near the event horizon, which carry energy away from the black hole at the expense of its mass. Over time, a black hole losing energy through Hawking radiation will slowly shrink and eventually evaporate entirely. The timescale for this process is staggering. A stellar mass black hole, the kind left behind by the supernova death of a massive star with perhaps 10 times the mass of the Sun, will evaporate through Hawking radiation in approximately 10 to the 67th power years. A supermassive black hole like the one at the center of the Milky Way, with millions or billions of solar masses, will take longer, up to 10 to the 92nd power years for the largest ones. These timescales are so vast that the stelliferous era, already incomprehensibly long, fits within them the way a single heartbeat fits within a human lifetime. But Hawking radiation is relentless. Given enough time, even the supermassive black holes will evaporate. The last black hole in the universe will lose its final remnant of mass in a burst of radiation, a brief, intense flare of gamma rays and particles representing the complete conversion of that final mass to energy. And after that, the black hole era ends. What remains? An extremely thin, cold, nearly uniform distribution of elementary particles, electrons and positrons and photons and neutrinos drifting through an expanding, cooling universe separated by distances so vast that meaningful interactions between them will become increasingly rare. This is the beginning of what cosmologists call the dark era, the final, essentially permanent phase of the universe's existence, in which no stars burn, no planets orbit, no chemistry proceeds, and the universe slowly approaches thermodynamic equilibrium. Thermodynamic equilibrium is the endpoint implied by the second law of thermodynamics, the principle that entropy, the measure of disorder or sameness in a system, always increases over time. A universe in perfect thermodynamic equilibrium is a universe in which everything is at the same temperature, in which no gradients of heat or density exist, in which no work can be extracted from any process, because work requires difference, and difference has been erased. This state is called heat death, not because it is hot, but because the heat has been distributed so perfectly uniformly that it is useless, cold even, featureless, eternal. The universe is moving toward heat death, has been moving toward it since the moment it began. The entire history of stars and galaxies and planets and life, every event in the 4 billion years of terrestrial biology, every moment of human civilization, every future epoch of red dwarfs and white dwarfs and black holes is part of the long, slow, inexorable approach to this final state. The James Webb revision does not change the destination. Heat death is not avoided or accelerated by the updated star formation models. The endpoint remains the same: perfect thermodynamic equilibrium at some point in the incomprehensibly far future. What the revision changes is the path. Specifically, it changes the density of events along the path, the number of stars, the richness of the stellar ecology, the duration of each phase are in subtle ways that accumulate from the stelliferous era forward. Think of it as a river. The river still reaches the sea. The destination is unchanged. But the Webb revision tells us that the river is running slightly faster through certain sections than we thought, eroding its banks somewhat more vigorously in the early miles, arriving at certain points downstream with slightly less water than the old maps predicted. The sea is still there. The river still reaches it. But the journey is shorter than we drew it. Now let us return to something that has been implicit throughout this entire account, but deserves direct examination. What does the Webb revision mean for the possibility of life in the far future of the universe? This question is not answerable with certainty. It may not be answerable at all given how little we understand about the origin of life and the minimum conditions it requires. But it is worth asking honestly, because it is the question that gives the Webb findings their most direct human relevance. The reason that a correction to the cosmic timeline matters to any person lying awake at night thinking about what will become of everything. The relevant framework here is the concept of habitable epochs, the idea, developed by researchers in astrobiology and cosmology, that the universe's history can be divided into periods during which the conditions for life to arise and persist were present, alternating with periods during which those conditions were absent. We currently live in one such habitable epoch, the middle of the stelliferous era, when stars are abundant and planetary systems are common, and the universe is at a temperature and density that allows biology to function. This epoch will not last forever. The sun will die. The habitable zone of the solar system will shift, then collapse, then vanish as the sun cools to a white dwarf. Other stars will suffer the same fates on their own schedules. The universe will gradually deplete its stellar population, and the density of active, habitable zones will decline. There may be secondary habitable epochs, around white dwarfs, around dim red dwarfs in the deep future, but they will be sparser and eventually non-existent. The total duration of all habitable epochs added together represents the universe's life-supporting window. Not the window in which life actually exists, we do not know that, but the window in which it could exist. in which the physical conditions necessary for biology are present somewhere in the cosmos. The Webb revision, by reducing the population of late-phase red dwarfs and their white dwarf remnants by a small margin, and by shifting the end of the stelliferous era approximately 2 billion years earlier, narrows this total window. The narrowing is not catastrophic. The habitable window is still vast by any human standard, but it is narrower than we thought. And the narrowing is not evenly distributed. It falls most heavily at the far end in those last trillions of years when only the dimmest, longest-lived red dwarfs are still burning. There is a philosophical dimension to this that is worth sitting with. We built our timeline from observations. We gathered light from across the universe, analyzed it, modeled the processes that produced it, and constructed a detailed picture of where the cosmos was going. We did this carefully, over decades, with instruments that were the best we could build. And we arrived at a schedule that felt, if not certain, at least well-grounded. The James Webb Space Telescope showed us that the schedule was wrong. Not dramatically wrong, not wrong in its foundations or its methods, but wrong in a specific direction. Early star formation was more vigorous than we thought. The budget was being spent faster than we calculated, and the end point was closer than we had drawn it. This is not a reason for despair. It is, if anything, a demonstration that we are doing something right. The scientific process, build a model, test it against observations, revise it when the observations don't match, worked exactly as it is supposed to work. The universe surprised us, and we updated our understanding. That is what science is for. But it is also a reminder of something that is easy to forget when you are surrounded by the confidence of well-established theories and precisely calculated timelines. The universe does not care about our models. It runs on its own rules, at its own pace, with its own schedule. Our job, the job of every scientist who points a telescope at the sky, every theorist who builds models of cosmic structure, every person who lies awake wondering what will become of everything, is to read that schedule as accurately as we can, to accept corrections when the universe offers them, and to hold our knowledge with the appropriate mixture of confidence and humility. The James Webb Space Telescope gave us a correction. We accepted it. The timeline is updated. And now, having traced the revised timeline forward through the death of the last star, through the cooling of the white dwarfs, through the evaporation of the black holes, to the doorstep of the dark era and the approach to heat death, we come at last to the question that all of this has been building toward, not a question about what happens next. We have covered what happens next in as much detail as physics allows, but a question about what the revision means. Not just for the timeline, not just for the cosmological models, but for us. For our understanding of where we are in the universe's story, how much of that story remains, and what it says about our place in the brief, burning, impossibly fortunate moment of cosmic time we currently inhabit. Because here is what the James Webb Space Telescope found, stripped of all the technical language and the large numbers and the careful caveats. The universe burned brighter at the beginning than we knew. It was younger and already older than we thought. It spent itself more freely in its youth, converted its raw material into light and heat and stellar fire at a pace that our models, for all their sophistication, had underestimated. And the consequence of that early extravagance is that the long, patient, twilight future we had penciled in, the trillions of years of dim red dwarfs and cooling white dwarfs and slowly fading remnants, is a little shorter than we believed. The universe is not running out. Not soon, not in any time frame that human language can make personal, but it is running, and the running is faster than we thought, and the tape is shorter than the old measurements suggested. That is what the revision means. Not doom, not emergency, not cause for the kind of existential alarm that makes for dramatic headlines, but cause for reflection, for recalibration, for sitting with the knowledge that the universe we live in is still, despite all we have learned, surprising us, still revealing itself to be something slightly different from what we expected. The James Webb Space Telescope is still operating. It will continue to collect data for years, possibly decades. The early galaxy findings are not its last word. New observations are being analyzed. New papers are being published. New surprises may be waiting in the data, anomalies that will force further revisions, further updates to the schedule, further corrections to the timeline we thought we had right. What those surprises will be, we cannot know. That is precisely what makes them surprises, but we know where to look. We have the most powerful observatory ever built, pointed at the deepest and earliest parts of the observable universe. And we know what we are trying to understand, not just what happened then, but what it means for everything that comes next. That is where we are going in the final section of this story. Not further into the far future. We have traced that arc as far as the physics allows, but back to the present moment, to the question of what it means to know that the timeline is shorter than we thought, to the question of what the James Webb Space Telescope is still telling us and what it may yet reveal, and to the question of what all of this, the revised timeline, the updated schedule, the cosmic clock running 2 billion years fast, says about the nature of the universe we live in and the nature of our capacity to understand it. There is something strange about the moment we are living in. Not strange in the way that every moment in human history has seemed strange to the people living through it, not the strangeness of political upheaval or technological change or the ordinary turbulence of civilizations in motion. Strange in a deeper, quieter, more permanent way. Strange in the way that only becomes visible when you pull back far enough from the immediate to see the whole shape of the thing. We are living in the only period in the history of the universe when it is possible to observe the universe as it actually is. That sentence requires unpacking because it is not obvious, and the James Webb Space Telescope has made it more urgent than it has ever been. The universe is expanding, has been expanding since the Big Bang, will continue expanding for as long as physics allows any prediction to be made. And the expansion is accelerating, driven by dark energy, the cosmological constant, whatever it is that fills the vacuum of space and pushes galaxies apart at an ever-increasing rate. The consequence of this acceleration is that galaxies beyond the local group are receding from us faster and faster, and the light they emit is being stretched, redshifted, and eventually will be stretched beyond any instrument's ability to detect it. Those galaxies will disappear behind a cosmological horizon, not because they cease to exist, but because the space between us and them will be expanding faster than light can cross it. This process is already underway. There are galaxies that we can see today, faint, distant smudges in the deepest images taken by Hubble and Webb, that are already receding faster than light. We see them because the light they emitted long ago when they were closer has had time to reach us. But no new light they emit today will ever reach us. They are already, in the only physically meaningful sense, gone from our universe. We are looking at their past, not their present. In the far future, This process will complete itself for all galaxies beyond the local group. The observable universe will shrink, not in absolute terms, not physically, but observationally, to just the local group. Eventually, to just Milkomeda. A future civilization in that merged galaxy, if any exists, will look out into the darkness and see nothing. No distant galaxies, no cosmological structure, no evidence that the universe contains anything beyond their own small island of stars. They will be, observationally, alone in a way we are not. They will also, critically, be unable to reconstruct the history of the universe from observation alone. The evidence for the Big Bang, the cosmic microwave background radiation, the distribution of galaxies across cosmic scales, the large-scale structure of the universe will have been diluted and redshifted beyond detection. A future physicist in Milkomeda, working only from observations available to them, would have no direct evidence that the universe began in a hot, dense state. They might infer it from other reasoning, but the observational pillar on which modern cosmology rests will be gone. We are living in the window during which the universe is old enough to have produced stars and planets and life and minds capable of asking questions, but young enough that the evidence of its origins and structure is still visible, still detectable, still available to instruments like the James Webb Space Telescope. The window is not closing tomorrow. It will remain open for billions of years, but it is a window, not an infinite expanse, and the James Webb Space Telescope represents one of our most powerful efforts to look through it while we still can. This is one reason the early galaxy findings matter beyond their immediate cosmological implications. They are not just a correction to a timeline. They are a piece of evidence gathered in the window, information about the deep history of the universe that will eventually become impossible to gather. The light from those distant, early, unexpectedly massive galaxies has been travelling for over 13 billion years to reach Webb's mirror. That journey began when the universe was less than 1 billion years old. The galaxies that emitted it have long since evolved, merged, aged into something unrecognizable from their early form. We see them as they were, not as they are. And what we see tells us something about the rate at which the universe spent its early resources, something that has consequences for the entire future timeline. But the window also means something else, something more personal, if you allow yourself to think about it in those terms. Every observation the James Webb Space Telescope makes is, in a sense, irreplaceable. Not because the telescope is unique. We will build better telescopes, more powerful instruments, wider arrays, but because the universe itself is changing. And the information it contains is not static. The distant galaxies are moving away. The cosmic microwave background is cooling, its signal weakening relative to the noise floor of observations. The large-scale structure of the universe, the filaments and voids and galaxy clusters that trace the original density fluctuations from the Big Bang, will be diluted by the ongoing expansion. Future astronomers will have better instruments, but a less information-rich universe to point them at. We have worse instruments, but a richer observational landscape. The James Webb Space Telescope is operating at a moment of unusual privilege in cosmic history. Not the most privileged moment, that might be 1 billion years from now, when instruments we cannot yet imagine will look at a universe still observable in its full structure. But a privileged moment nonetheless. And the data it is returning is already changing our understanding in ways that matter. Consider what we have covered in the arc of this story. We began with a settled number, 13.8 billion years, the age of the universe, and a settled timeline, the schedule of cosmic events that represented our best pre-Webb understanding of where everything was going. We traced the early galaxy findings, the anomalously massive and bright objects in the deep fields of Webb's first observations, the tension between those observations and the predictions of the standard cosmological model. We followed the implications of that tension forward through the stelliferous era, past the death of the Sun and the merger of the Milky Way with Andromeda, to the declining rate of star formation and the slow depletion of the universe's hydrogen budget. We traced the correction, the approximately 2 billion year shortening of the stellar era's far end, through its specific mechanisms. Faster early star formation means more rapid depletion of the gas reservoir. Faster depletion means fewer late-forming red dwarfs. Fewer late-forming red dwarfs means the last stars die sooner. The stelliferous era ends 2 billion years ahead of the old schedule. We carried the story into the degenerate era, through the cooling of white dwarfs and the theoretical possibility of secondary habitable zones around those cooling remnants, through the evaporation of black holes via Hawking radiation, to the dark era and the approach to heat death. We noted how the Webb correction ripples through each of these phases, not dramatically, not catastrophically, but consistently, a persistent narrowing of the universe's remaining abundance. And now we are here, in the final section, which is not about what happens next in the timeline, but about what the story of the timeline means, what it tells us about where we are, what we are doing here, and what the James Webb Space Telescope is in the process of revealing. Let us start with what the telescope is still doing. As of its current operational status, Webb is in its primary science phase, collecting data across multiple observing programs simultaneously. The early galaxy findings that sparked the timeline revision were generated largely from the JWST Advanced Deep Field Observations, long exposures of relatively small patches of sky designed to collect light from the most distant, and therefore earliest, objects in the observable universe. Those observations are ongoing. New data continues to arrive. The analysis is nowhere near complete. Some of the most dramatic early findings have already been refined. Galaxies that initially seemed impossibly massive have been re-examined with spectroscopic follow-up observations, the technique of dispersing their light into its component wavelengths to get precise redshifts and chemical compositions. And some have turned out to be somewhat less extreme than the photometric estimates suggested. The error bars have been tightened. The population of genuinely anomalous early galaxies is somewhat smaller than the initial reports implied, but it has not disappeared. The core finding, that the early universe was forming stars at rates our models did not predict, that some early galaxies were more massive and more evolved than the standard model expected, has held up through scrutiny. It is real. The revision is real. The models need updating, and the updating is in progress. What the updating looks like, in practice, is a series of adjustments to the parameters that govern star formation efficiency in cosmological simulations. These simulations, vast computational projects running on some of the world's largest supercomputers, model the formation and evolution of galaxies from the Big Bang to the present, tracking the behavior of dark matter, gas, stars, and black holes across billions of light years and billions of years of time. They are the most sophisticated tools we have for understanding the universe as a whole, and they are imperfect. They include subgrid models, simplified representations of physical processes that occur at scales too small to resolve directly in the simulation. And those subgrid models are where the adjustments are being made. Specifically, the models of stellar feedback, the processes by which young, massive stars and supernovae heat the surrounding gas and disrupt star-forming regions, are being revised. The Webb data suggests that in the early universe, stellar feedback was either weaker than the models assumed, or that some mechanism allowed star formation to proceed at high efficiency despite feedback. Perhaps the early universe's denser, more turbulent gas clouds were less susceptible to disruption. Perhaps the very first generation of stars, lacking the heavier elements that modern stars carry in abundance, had different feedback properties. Perhaps dark matter halo dynamics in the early universe created conditions that concentrated gas more effectively than later halos. All of these hypotheses are being explored. None has been definitively confirmed. The field is in an active state of productive uncertainty, the best state for science to be in. But there is a broader implication here that goes beyond the technical details of stellar feedback models. It concerns the reliability of long-range prediction in cosmology and what the Webb correction tells us about the limits of what we can know about the future. We have been talking about a 2 billion-year revision to a timeline that extends for tens of trillions of years. That is a correction of about 0.02%. In most contexts, a prediction accurate to within 0.02% would be considered an extraordinary success. The models were not wildly wrong. They were slightly wrong in a specific place, the early universe, in a way that propagated forward to produce a modest revision to the far end of the timeline. But here is the question that honest cosmology must ask. If the models were wrong about the early universe, and we discovered that wrongness only because we built a telescope powerful enough to see into the early universe clearly for the first time, what other wrongnesses might be waiting in regions of parameter space or epochs of cosmic time that we have not yet been able to observe clearly? The far future of the universe, the deep stelliferous era, the degenerate era, the black hole era, cannot be directly observed. We cannot send a telescope to the year 10 trillion and look back. We can only model it, extrapolating from the physics we understand and the observations we can currently make. The models we use are the same models that missed the early star formation efficiency. They have been improved, yes. The Webb correction is being incorporated, but they remain models, built on assumptions calibrated against observations that are necessarily limited to the present and the observable past. There may be other corrections waiting, other places where the model predictions, extrapolated into cosmic futurity, are running ahead of or behind the reality that the universe is actually enacting. We do not know where those corrections are or in which direction they will push the timeline, because by definition, we have not yet found them. They are the unknown unknowns of long-range cosmological prediction. This is not a counsel of despair. It is not an argument that cosmology has failed or that long-range prediction is impossible. The models are genuinely good. They are built on solid physics and tested against enormous quantities of observational data. The 2 billion-year correction is a refinement, not a refutation. The framework stands, but the framework now carries, explicitly and honestly, a somewhat larger uncertainty than it did before Webb turned on. The error bars on the timeline's far end are wider, and they will likely get wider still as Webb continues to observe, as future telescopes build on its findings, as the early universe is mapped in increasing detail, and the models are pushed to account for what they find. This is good. Wider and more honest error bars are preferable to narrow and overconfident ones. A science that knows the limits of its predictions is more trustworthy than one that does not. Now, let us bring this home. Not to the abstract level of models and error bars and cosmological parameters, but to the level at which the timeline means something to a human being thinking about it in the dark. You are here, right now, in the present moment, 13.8 billion years into the universe's existence. You are made of atoms forged in stellar interiors. The carbon in your body was produced in the nuclear reactions of stars that died before the sun was born, scattered into the interstellar medium by supernovae, gathered into the molecular cloud that collapsed to form the solar system, incorporated into the chemistry of life on Earth over billions of years of biological evolution. You are, in the most literal physical sense, a product of stellar fire. You are made of the stelliferous era. You are it looking at itself. The universe you inhabit is 13.8 billion years old and has, according to the best current estimates, now updated with Webb's corrections, somewhere in the range of tens of trillions of years remaining in its stellar era alone, before the last fires go out and the long darkness of the degenerate era begins. You are living at an extraordinary point in the universe's history, late enough that complexity and chemistry and biology have had time to emerge from the early chaos, early enough that the universe is still rich with energy and structure and burning stars. The Goldilocks moment of cosmic time in a very loose sense, not the only moment when life is possible, but among the most favorable. And you are living at the moment when a telescope built by your species, assembled in clean rooms by human hands, launched on a rocket designed by human minds, programmed with observation schedules constructed by human scientists, looked further into the past than any instrument before it, and found something unexpected, found galaxies that were too big, too early, found evidence that the universe had been doing things faster than the models predicted, found a correction to the timeline. That correction is 2 billion years. Taken off the far end of the stellar era, which itself ends tens of trillions of years from now. It does not affect anything that will happen within the lifespan of the Sun. It does not affect anything that will happen within the lifespan of human civilization, however long that turns out to be. It is a purely cosmological fact, relevant only on timescales that no human will ever experience directly. And yet it matters. It matters because the universe is not a story we tell. It is a story that is actually happening, has been happening for 13.8 billion years, will continue happening for incomprehensibly longer. And the schedule of that story, the timeline of its phases and its events and its endpoints, is the structure within which everything that has ever existed or ever will exist is embedded. Getting the schedule right is not an academic exercise. It is the deepest form of honest attention we can pay to the world we live in. The James Webb Space Telescope paid that attention. It looked at the early universe with instruments precise enough to reveal what the models had missed, and it found the discrepancy. And the discrepancy forced a revision. 2 billion years. A small number by cosmic standards, an enormous number by human ones, and an important number by the standards of intellectual honesty. There is one more thing worth saying before this story concludes. It is not a scientific point, but a philosophical one, and it concerns the nature of the project we are engaged in when we build telescopes and trace timelines and sit with the incomprehensible vastness of cosmic time. The universe does not need us to understand it. It does not require our attention. The stars burn whether or not anyone measures their spectra. The red dwarfs will persist for trillions of years, regardless of whether any mind exists to calculate their lifespans. The last star will die in darkness and silence, whether or not any civilization has ever constructed a model predicting when that will happen. The universe's indifference to its own comprehension is total and absolute. And yet we build telescopes, we do the calculations. We trace the timeline from the Big Bang to the heat death, update it when the data requires updating, and carry the result forward into papers and lectures and conversations and long-form narratives like this one, offered to anyone who wants to listen, who finds themselves unable to sleep and drawn toward the enormous question of what will become of everything. Why do we do this? Not from necessity, not because the knowledge is immediately useful in any practical sense. We do it because the questions are real and the universe is real and the human capacity for understanding, limited, imperfect, perpetually in need of revision but always reaching further, is one of the most remarkable things this universe has produced in its 13.8 billion years. We are the universe's most recent attempt at knowing itself. And the James Webb Space Telescope is the sharpest instrument that attempt has yet constructed. It has been looking at the sky for a few years now. In that time, it has found galaxies from the cosmic dawn, measured the atmospheres of exoplanets orbiting distant stars, peered into stellar nurseries with a resolution that reveals the earliest stages of stellar birth, and detected the chemical signatures of molecules in interstellar clouds light years across. It has returned data that has generated hundreds of scientific papers, revised models that had stood unchallenged for years, and given astronomers a view of the early universe that was simply unavailable before. And it has done one more thing, quietly, in the background of all that science. It has reminded us that the universe is not finished revealing itself, that the confident summary of what we know, however well supported, is always subject to revision when a better instrument looks at a previously inaccessible part of the sky. The timeline we have been tracing through this story, from the present, through the death of the sun, through the merger of galaxies, through the decline of star formation, through the death of the last red dwarf, through the cooling of white dwarfs and the evaporation of black holes, to the long darkness of the heat death, is the best timeline we have. Updated now with the Webb correction, carrying explicitly the uncertainty that correction implies, honest about what it knows and what it does not know. It is 2 billion years shorter than the timeline we had before the telescope turned on. 2 billion years have been trimmed from the far end of the stellar era, the long twilight of the last stars. The universe's habitable window is narrower by that much. The last fires will go out sooner, but the fires are still burning. Right now, in the present moment, the universe is full of them. Hundreds of billions of galaxies, each containing hundreds of billions of stars, burning in every stage of their life cycles, warming planets and driving chemistry and making possible whatever it is that the universe is doing with complexity and energy and time. The stelliferous era is not ending. We are deep within it, in its early chapters, with tens of trillions of years still ahead, even on the revised schedule. The clock is running, the budget is being spent, 2 billion years faster than we thought, but there is still an enormous amount of time on the clock, an enormous amount of light in the universe, an enormous amount of story remaining in a cosmos that has already surprised us more than once, and will, if history is any guide, surprise us again. The James Webb Space Telescope is still running its observations. The early galaxy data is still being analyzed. New anomalies are being catalogued. New papers are being written, new revisions to the models are in progress. The schedule may change again. The 2 billion-year figure may be refined, upward or downward, as the data accumulates and the analysis deepens. We will update the timeline when it does. That is what we do. That is what the science requires. That is what honesty, in the face of a universe that does not ask our permission to be what it is, demands. The universe is 13.8 billion years old. The last stars will burn for tens of trillions of years. The end is unimaginably far away, but it is 2 billion years closer than we thought, and the telescope is still looking.